we now have another talk, again in the direction of discussing which direction we need to go beyond the standard model physics in the future. And I think David will, with this title, will tell us, will give us many new ideas or new perspective on old ones. So the many frontiers of particle physics. As we did before, there is no strict limit on the time, but we want to have some discussion at the end. So, okay, the same as Adam's would be nice. Please.
Okay. Let's see. Yeah, hold on one second. Let me share in a different way. Let's see. Sound better. Okay. All right, one more second. 2 years, I still can't figure out Zoom. Can't see anything.
What's the problem?
I'm trying to get into a mode so that all of your faces are not covering the top of my slide.
Okay.
Look, this is unfair. I think
So I'm
Roberto
not a Zoom
comments,
expert, I have to admit.
Well, okay, I see how this talk is going to go anyway, so it doesn't matter if I can see it. Good.
Okay, let us know if you want to do something else. I can share it and then maybe move them if you prefer at some point.
Okay. No, it's fine. It's fine. Good. I'm going to talk based on my crappy response to John and Ricardo back in May in their very big talk. Roberto was very kind and brave to invite me to give a talk a little bit about what I think is the frontier of new physics, or where we should be looking, and maybe as opposed to LHC physics or in addition. So this is the talk I created. Let's see what happens. The unknown, our job as theorists, the theorists are supposed to parameterize the unknown. So we parameterize it by saying, for example, parameter energy. High energies are places where we have not collided particles, investigated arbitrarily high, and what could be there are new states, or that look like individual particles, or maybe strong coupling schmutz, or suppressed operators if you can't get to the direct production, as we talked about in Adam's very nice talk. And so here's a magnetic dipole moment operator, things like this, or access to even higher energies, the new physics. The other direction is weak coupling. That could be new light states, again, creating the particles, but are very light. And we haven't seen them yet because they're hard to create. The probability is low that it interacts with us. Or we see it in the sense of a new long-range force. It's such a light particle that it produces a even macroscopic interaction between standard model matter atoms. And then we could go as far as violating our sacred principles. We could violate Lorentz invariance, but when you do that in silly ways, you have to watch out for the impact on general relativity. You could violate the rules of general relativity. Typically, what you end up with are new fields, really just new long-range forces. It's hard to do something that's really distinct from that. Or even violating quantum mechanics itself, and there you have to watch out for everything to make sure what you're doing is sensible. Here's a new physics model, B minus L gauge bosons. We've all heard of B minus L gauge bosons. B minus L gauge bosons, maybe they're nice because B minus L globally is preserved in the standard model. You add a right-handed neutrino, which maybe we want, and you cancel anomalies for the gauge symmetry. They emerge from left-right models. They emerge from gut models, these U ones. And maybe it's involved in leptogenesis. Maybe it's involved in supersymmetry breaking, if you care about that. Neutrino matter effects, all kinds of interesting things could occur. So that's the theory. How do we search for it? Atlas is continuing to search for new Z's. Here are bounds, which on the left side is roughly the gauge coupling with some scaling of B minus L, and the red line is the constraint on the strength of that coupling as a function of the mass. And we've been able to put strong constraints on very heavy particles, few TeV. Of course, B minus L doesn't tell you what mass it has to be. That could be for some very model dependent thing. So maybe you want to go to much lighter masses. Much lighter masses, you're looking at much lower energy colliders, dominantly B factories or the previous incarnations of the colliders at CERN or Boraxino. These are different ways of putting constraints. But again, if you don't want a theory bias, you could go to much lower masses. And as you get to lower masses, of course, it becomes a particle that can be emitted by stars and the sun in particular, and supernova 1987A. Maybe it has some impact on atomic physics, other light things like G-2, but very light things like emission from stars. And if you keep going with no bias, you can ask about the possibility that it is extraordinarily light, which means it does become a long-range force, and we can put constraints on long-range forces because B minus L measures neutron charge. And so different types of matter have different neutron charge. It is an EP, equivalence principle violating force. And so this B minus L would be a force, for example, from the Earth to your experiment on the surface of the Earth, and it would be EP violating. And those things have been tested for very long ranges, which correspond to extraordinarily light masses for B minus L. Fine, that's one theory, very broadly stated with parameters not fixed. But you can ask, what are the deep reasons to look for the new physics in B minus L? Maybe we should be guided by more deep fundamental reasons for doing that. And that's the reason why we get excited about certain LHC searches, because we're trying to solve something deep. So the Higgs, for example, has been understood to be problematic in the sense of our expectation of the dynamics around the Higgs. The cartoon child version of this story is always the fact that you calculate loops, and in perturbation theory, you expect contributions to the Higgs mass which are bigger than the Higgs itself in the standard model with some high cutoff. You've all heard that before. The solutions to such a fine-tuning is to remove the fine-tuning by saying there is new physics and it's at the same scale as the Higgs mass. Those are supersymmetry, composite Higgs, or Technicolor was before the Higgs was discovered. Large extra dimensions is effectively the same thing. It's the end of standard field theory, or the effective field theory we know, at the scale of the Higgs. And this solves the hierarchy problem by removing the hierarchy and putting stuff there. If you don't have stuff there, you could imagine solving the problem using a relaxation mechanism like the relaxion, where the Higgs mass is a dynamical parameter, and the reason it's light is because its magnitude, its physical value evolved in time through a very long age of the universe. And when it got to a critical value, say something very close to 0 compared to the natural scale, it stopped for some reason, for some dynamics. And the third possibility that we talk about or know about is an anthropic explanation, which is simply that there are varying Higgs masses all over the space-time or the Hilbert space or something. And there are dynamics in all of those places, and the dynamics here are things that can produce humans that ask such questions. And so when we talk about the deep motivation for understanding the Higgs mass, understanding electroweak symmetry breaking, and the fine-tuning that appears with the hierarchy problem or the naturalness issue, one is these high energy theories, which the LHC is probing, but perhaps the deep theories are, or the deep explanation for this problem is answered in the other direction, meaning theories with weak coupling. So that's something like a relaxion, but light particles, weakly coupled, that take advantage of long time scales in the early universe. Something more serious in the hierarchy problem is dark matter. More serious in the sense that there's more of a guarantee, there's more emphasis on the fact that the standard model is incorrect, that there's something there experimentally. So we can ask, the deep reason we go after dark matter is because it exists, and we don't have a description of it. That's good enough. It exists in the sense that we've measured it better than other physical quantities or objects that we've convinced ourselves exist. Its gravitational dynamics are clear. Its lack of non-gravitational dynamics, say in the cosmic microwave background, are borne out. And our simulations of toy versions of dark matter that only have gravitational dynamics, at least at moderate and large scales, look just right. So we have the strong evidence that there's dark matter, and we've essentially ruled out baryonic matter to an uncountable number of sigmas. So that is a question we're supposed to answer. What is it? Well, we say that dark matter, let's say, is made of bits, reductionist down to a fundamental object, a collection of which makes up all of dark matter, and we don't know what those bits are. And so there's a number line with all possible masses for these bits. The bits can't be lower than 10 to the minus 22 electron volts because quantum mechanically, their Compton wavelength or de Broglie wavelength don't fit inside of dwarf galaxies. And on the other hand, if they're bigger than 10 to the 6, 10 to the 8, maybe solar masses, they also can't fit in galaxies. They can't populate, at least create a distribution within galaxies, because they're getting close to the mass of these dwarf galaxies themselves. But anywhere in between, which is 100 orders of magnitude, are possibilities for the objects that could be dark matter. We've been going after the WIMP miracle, the majority of human power, financial effort, human hours, time, thought, intellectual effort on the theory and experimental side has gone into WIMPs, WIMPs being motivated by the WIMP miracle. And if you look at the thickness of the blue line, that is the extent to which we're covering this parameter space, at least the mass part of the parameter space. Not to mention the coupling, which we have scanned with beautiful experiments over decades, over a decade of possible cross sections or couplings. But in terms of simply what could dark matter be made of, this is clearly dominantly motivated by theoretical bias and by the fact that if you're an experimentalist and you can only do, let's say, 3 or 4 major experiments in your life, you're going to pick what the theorists say are the #1 possibility for how you would discover dark matter. And so the distribution of the probability of what dark matter is doesn't line up precisely with the distribution of effort, because each experimentalist is deciding what's good for them. Now, broadly, you can ask, is there a WIMP miracle? Well, there's nothing at the weak scale besides the Higgs so far. There certainly could be. There's motivation for it, but it is not the kind of motivation that existed before when you really wanted to explain the hierarchy problem and fine tuning. And so it's clearly weaker, and a lot of parameter space is also ruled out. And there are plenty of models for producing dark matter of different masses with the right abundance all over the place, different types of.
Sorry, can I say something, or should I?
Of course.
No, in your narrative, you're saying as if the miracle was, a weakly attracting particle or a mass around 100 GeV, which 100 GeV is the natural scale of supersymmetry in the late 80s. Okay.
Correct.
But if people had been more honest in the late 80s, they would have admitted that the WIMP miracle is more like particles in the few TeV range. But at that time, the expectation of supersymmetry in the 100 GeV range, because a weakly couple part like a Higgsino or a Wino, just take weak coupling, is TeV or several TeV, a range which we have not yet directly tested. So,
Okay.
right. So in a sense,
Yes,
yeah, I mean,
I would say that the WIMP miracle, the reason you get excited about it is because there's a coupling that's roughly predicted, which is electroweak coupling, and then a mass scale that's roughly predicted, and you get the right abundance. And lo and behold, it looks like something associated with electroweak symmetry breaking.
If you look at the genuine electroweak cup, yeah, they were doing B-node, then you just turn around it. But if it is, unless it's a B-node, then the mass goes up very quickly.
Yes.
You should
No, in
temper
fact,
it. So
yeah, the original WIMP is a vector-like neutrino that couples to the weak interactions, and it was already ruled out by the time the WIMP miracle. Yeah.
But maybe this WIMP miracle should have been seen more as a broad window rather than a narrow thing. And
Sure.
then if you see it that way, it's not such a great miracle, but still interesting, and it's not that much ruled out. Okay, this is all I'm saying. If you de-emphasize its importance, you also de-emphasize its being now in trouble in a sense.
I completely agree. And that's really what I wanted to say, which is that it's less important. But if it's less important, there are many other ways that dark matter could come up with the right abundance with relatively nice couplings. And yes, this one's close to the weak scale. And yes, these couplings are reasonable, but you can make them whatever you want. But it doesn't motivate the vast majority of the effort to look just for the WIMP, is all I'm saying. You see what I mean?
Sure.
Yeah.
Sorry, David, I kind of agree with most of the things you say, but concerning the just dark matter being a thermal relic, I don't think the situation is much different from before. I mean,
yeah,
it's less compelling supersymmetry, but a triplet of SU2 is as compelling as before.
Sure, but this is what we were saying before, Michele.
Yeah. Okay.
This is another way of phrasing what we were saying, right?
Okay.
Yeah,
you can criticize as much as you want supersymmetry, but I think.
Yeah, I would say.
Yeah, I think David is building on the wrong perspective of the past to make his criticism.
Okay. No, of course. But I agree about everything.
But this rhetoric is not completely bold.
Look, what I'm saying is I put a number line, and most of the effort has gone to one spot on the number line. And yes, there are nice models there, but the models don't knock you on your ass. You look at it, you say, "Oh yeah, you can fit. Yeah, it's pretty nice." You know.
But look, I mean, simpler than a triplet of SU2. Okay. For that matter, there is nothing, except maybe it's excluded, but
maybe indirect bound from diffuse, gamma ray, stuff like this, but direct searches.
No, indirect searches. Okay. People in the States claim that indirect searches exclude the triplet of SU2.
But do you agree?
Anyway.
Do you agree?
Me? Well, I don't know. It depends on astrophysics, which is complicated.
Oh, you mean indirect search, not direct? Yeah, I mean
no, indirect.
Okay, indirect.
Yeah, indirect.
Anyhow, yeah. But I think this is still one of the simplest model of dark matter.
I think so.
It's complete. So. Is simple.
I think so, but so is vacuum misalignment.
No, but then okay.
I'm just saying that it's not a model with a small parameter space that just predicts the right amount of dark matter. It's a model with a large parameter space that can very comfortably accommodate the right amount of dark matter. That is all I'm saying. And because of that, it's probably worth putting significant effort, in a more distributed way in searching for dark matter. That's my thing. You may feel emotionally attached to the weak. Something really should be there. It's important. That's what I believe. The hierarchy problem is solved at 10 TeV, which is fine. But I don't think you can make a quantitative, solid argument that only 10 to the minus 3 of effort should be put elsewhere in searching for dark matter. my statement. That's it.
We agree.
That's
on
what I'm
this.
trying to
I think pretty much everybody would agree on this, right?
Exactly. This is an early
So, but
slide.
I thought we would disagree more. Okay, but that's okay. So I'm
I
not
got it.
having fun.
I have 60 slides,
Okay.
so we're going to be yelling
Okay.
very soon, I promise. So I'm putting up this table. I hate when people put up tables, but I just want to make a simple statement, which is if you look at this potential list range, everything to the left of, for example, 10 to the 2 electron volts must be a boson because of occupation number of dark matter in the galaxy. And so bosons can be spin 0, spin 1, perhaps spin 2 with some range before you get to the strong coupling. And so that's a nice chunky 24 order of magnitude range of possible dark matter candidates. And one reason you wouldn't want to try to test any part of this range is because you could imagine any possible coupling could be true. And that means it would be very hard to decide how to test anything. This is just too big of a parameter space. But for lighter dark matter, for things that are bosons that are, say, below mass of 100 electron volts, you can write all of the leading operators for all of the possible spin 0, spin 1, and spin 2. And then you can ask what the physical effects of those leading operators are on standard model particles. And half of them are just precession of spins, effectively, is the physical effect. And you can build experiments to look for precession of spins in a wide range of frequencies and therefore masses. A third of them are basically just forces, the scalar or a vector, a B minus L like thing, or a spin 2, which couples to matter in the way a graviton would couple. These are just forces. So if you have accelerometers, like gravitational wave detectors, or the things they do in Seattle, those are going to be very sensitive tests to dark matter for these types of couplings. You can have electromagnetic effects, basically fancy versions of LC circuits, which is what ADMX is, but those sorts of effects are also covered for light scalars or pseudoscalars or vectors. And you can have the effect where the mass of the electron, for example, or fundamental parameters change, oscillate in time, and that can affect things like atomic clocks, transitions in atoms, and higher order effects. So it's not like there's a semi-infinite number of ways to test the physical effects. There's a handful of ways to test the physical effects. And that's important because it means that maybe you say, fine, I don't know what I think of scalar dark matter, but if I have an experiment that can cover 10 orders of magnitude in mass and 10 new orders of magnitude in strength, then I would say it's worth doing, especially if it's a scale much smaller than, say, xenon n ton. And there are these types of experiment, the Etwash experiment, these torsion balance experiments, which are studying EP violation from static forces, would also see the force of a dark matter wave moving through if it was made of a scalar or vector or things like that, that would cause EP violating forces. The Magis experiment in Fermilab, which is a precursor to a gravitational wave detector, may not be sensitive to many gravitational waves in this incarnation, but will be sensitive to, and will be roughly the second red dotted line in the right-handed graph for testing light bosonic dark matter. So I find these things very interesting, and this is a kind of sensitivity which I think is important to build. On the left graph, it's a scalar dark matter, and it's hard to get there, but if you can get to that diagonal line in the bottom right corner, that is the naturalness line. That's where the scalar coupling does not renormalize the mass beyond its natural value. And beyond that line, of course, is where the relaxion lives, for example. So if you like relaxion models, you want to think about experiments that can push past that line or that line in other contexts. if you have light scalars, you have potential versions of dark matter, but light scalars also produce new forces. And so just as a side note, something that Sergit Georgiou-Grada and I thought about was the fact that the old-fashioned Mossbauer experiments, which were clever ways of measuring very precisely nuclear transitions, could actually measure new scalar forces at much shorter distances than normal short distance gravity experiments. And that's because if there's a new scalar force, matter will source a scalar field. A scalar field couples to matter in such a way that if you turn it on, it changes the mass of particles. And so you can change nuclear transitions by having matter very close to those nuclei, just from the sourcing of the scalar field. You change the potential for the scalar field locally, you change the nuclear transition, and if you move that source around, you could potentially detect it with Mossbauer, very old-fashioned experiments. You know, we tried to email all the experts in the type of Mossbauer that we thought would be relevant, but most of them were dead because these experiments were perfected in the 1960s, and then they had other ways of doing spectroscopy.
So what did they answer?
as you expect. But there are new versions. There are very crazy things people are doing with Mossbauer experiments now. They're exciting nuclear transitions by stimulating them using X-rays or using what is it called? You know, electrons going in a circle, synchrotron radiation at high frequencies. And they've already shown beginnings of this possibility, but they may be able to really amplify the yield that you get out of these transitions from Mossbauer experiments. But even without that far future sort of set of ideas, this is a way that you can probe very short distance forces, which right now are constrained to be not weaker than gravity, much stronger than gravity. And in this case, GeV is a trilinear coupling of the scalar field to the Higgs. So sort of the Higgs portal, and that brown line, below that brown line is the parameter space of the relaxion. So these type of experiments, the black line and the green line, can probe already into parameter space where you have natural scalars coupling to matter with quite weak couplings.
So here you're not committed to any relaxation model. You say relaxation by being something coupled to the Higgs weakly enough not to.
Exactly. I asked.
Not this or that relaxation model.
I don't care. Yeah, it's just the idea that there's a light scalar and it's involved in some dynamics with the Higgs mass. Let's try to couple to the all possible masses. And this is a range of masses that these type of experiments can do and get already across this line. All right. Dark energy. What is the deep motivation for dark energy? Well, we measure an accelerated expansion of the universe. It implies potentially a cosmological constant. Whether or not that's a cosmological constant, there's an insane tuning associated with the vacuum energy. Again, in the perturbative diagrammatic way of stating it, there are all kinds of contributions to the vacuum energy, divergent, finite, phase transitions, classical counter terms. All of these things contribute in ways that are much larger, of course, than the measured implied value of the cosmological constant. And this is this crazy fine tuning. And for years, you hope to wash this away so that you can focus on the hierarchy problem. And so, oh, gravity is very strange. Of course, it's not very strange at low energies. We understand it quite well. Or how can you calculate you're in curved space? There's a back reaction. Of course, that's not true because the curvature that you produce by a cosmological constant lambda is suppressed by 2 powers of m Planck. So you're doing calculations in effectively flat space at short distances and getting contributions to the vacuum energy. You say UVIR, dude, maybe there's some deep connection to it. Maybe there is. I've been hearing that for 30 years and I can't say anything about it. Here's one UV-IR connection, anthropics. Maybe there's many possible versions of the cosmological constant across a much larger space-time or a Hilbert space or something. And this is a historical solution. We have the cosmological constant we do. And Weinberg showed that that's a pretty good cosmological constant. It's predicted almost by anthropics if you fix all other initial conditions like the perturbations in the initial condition. If you don't fix that, then you get different values. But it's a broad argument that perhaps we're sampling, and by existing, we're sampling the small cosmological constant region of a much larger universe. Absolutely could be true. The other natural question is, can you do the same thing? Can you relax like we do for the hierarchy problem in the relaxion? Can you relax the cosmological constant? If you have a very flat potential and you focus in on the region where you're close to zero vacuum energy, it looks like just a simple linear potential. And we're asking the question, why now are we here where the vacuum energy happens to be very tiny after this field perhaps has scanned lots of possible values of the cosmological constant? This is the simplest, dumbest solution of the cosmological constant, and it already mostly works with doing very little. You have a slowly rolling field, and it rolls slowly because of either Hubble friction or perhaps there's other types of friction coupled to other fields. And you roll very slowly, and you roll over many ages of what we call the age of the universe today. The universe is massively inflated, mostly empty. Soon after that scalar field value crosses zero vacuum energy, the universe contracts, and the flatter that potential, the smaller the cosmological constant is when the universe contracts. That rolling can take forever, but if the universe contracts and then re-expands, that happens in roughly a Hubble time today. And that's a very short time. So you can imagine phi rolls a very long distance, tunes the cosmological constant, triggers a contraction. And if the universe is allowed to re-expand for some magical UV physics, you have Big Bang cosmology, a tiny cosmological constant, and a scalar field, which is very light and potentially rolling today. I'm not going to go through this whole history. This is from a different talk. But what you imagine is that the universe spends a very long time CC dominated with a very slowly rolling field. And what triggers the end of this rolling epoch is that the scalar field crosses zero, contracts the universe, and by doing so reheats all of the energy density in the universe, namely the kinetic energy of the scalar field and what else it couples to. And then if you allow for the possibility that the universe goes from contraction to expansion and doesn't hit a singularity, perhaps you need to violate the null energy condition to do that at that point. But if it does that, you now have expanding universe in Big Bang cosmology and a tiny cosmological constant.
So why should the field remain there across this phase
So
that
you
we have
can-
no idea what we are doing?
Good. So you can, why should the field remain
Yeah,
there?
I mean, can you show me how this field remains?
Yeah. So
Why should the cosmological constant remain small across this song and dance, this sound and fury of, this
Yes.
part of the...
Yeah. So what you're doing before you get to the contraction phase, you have a very homogeneous evolution for this field. And then you begin to contract. And in the contraction phase, you blue shift the kinetic energy of that rolling field. And you can compute the fluctuations of that field. The fluctuations are spatial, not in phi dot. Those fluctuations are extremely tiny. They're of order whatever the Hubble scale is at that time. And during contraction, they leave the horizon too. So you're really dominated by just the homogeneous kinetic energy of phi. But you can compute and show that if your kinetic energy dominated, that the distance phi rolls is actually proportional to the log of the scale factor of the contraction from where you start to where you end at short distances. And then if you couple the scalar field to other degrees of freedom, say radiation degrees of freedom, then you can also show that typical in these models, the scalar field feels additional friction due to the thermal bath. And that additional friction even slows the scalar field down more, such that it really doesn't move anywhere. It stays both homogeneous, but essentially fixed during this contraction and expansion.
So the field does not have any coupling to curvature or stuff like that.
The field could have, Planck suppressed coupling to curvature in principle. Although this field, we've broken, any shift symmetry associated with this field by its potential. Sure. And so we're dominating, we're saying that any other couplings like that, they have to be proportional to this very tiny potential. Well, all of this is to say that if there is a cosmological constant solution that's associated with a very slow tuning, the simplest scenario of this kind is where the field, I don't have to construct extra barriers.
Yeah, I understand, but the problem, I understand. The problem is that you can go through this, and then you have to bounce back, right? And to bounce back, you have to violate an energy condition.
The UV bounce, yeah. So then you can ask, does the UV bounce with it, which is a short distance phenomenon, and high Hubble scale or short Hubble radius, does that have a dramatic effect on phi? Now you can say to me, well, I'm above the valid effective theory, so perhaps this causes a phase transition. And that's absolutely possible. If that bounce causes a phase transition in any part of the theory, that completely screws up the cosmological constant tuning. But if it does not, if this bounce allows you to return adiabatically to the same field configuration for all the fields involved, then you wouldn't. Then phi is essentially stuck there.
Yeah. But this is similar to what also Paolo, Pirtkalava were doing, right?
Yeah, in their case, they created a trigger and then injected NEC violating effects to dump energy into the system.
And I remember the assumption they had to go through in this next phase were pretty extreme, right? But that's okay.
Yes, but the difference between them and this one is that in their case, they're at this long Hubble wavelength. They inject energy into the system and make the claim that they can now heat up the universe to non-trivial temperatures, meaning change the Hubble scale dramatically. And we're not doing that. The only reason we need NEC violation in this story is that you just need to turn around the evolution of the scale factor. We're violating energy conservation because we use gravity. Gravity violates energy conservation. The contraction of the universe will give us
the null energy condition period.
But the null energy condition here is not for that reason. It's to change the direction of the evolution of the universe. You see what I mean? So you're contracting, go to higher and higher energies, and now I need something that contribute to the Friedman equation such that you start
the field theory is very unusual, and whether that makes sense. Well, okay, that's it.
Of course.
More than unusual. Okay.
Do you know how matter gets out of black holes? There's some way that matter gets out of strong gravity. So either there's an effective field theory description of a bounce.
The method that gets out of black hole is already out of black hole because the wavelength of the thing coming out is a wavelength of the order of the horizon. So it's not saying there. It's coming from the region, but not. I don't know. Okay.
I'm asking an S matrix question, but fine. So, but let's just back up. Let's say, okay, that particular model is crap, but it is at least plausible that some model that tunes the cosmological constant would leave us with a rolling scalar field today. And if that's the case, then we should ask physically what the impact of a rolling scalar field today. So this is well known. A rolling scalar field today, of course, is changing the vacuum energy as a function of time. It also contains kinetic energy. So the equation of state of this scalar field, including the vacuum energy associated with it, is just this kinetic minus potential over kinetic plus potential. That's the pressure over the density. And you can estimate, calculate, numerically.
Of course, whatever source violated an energy condition is gone out of the game here, which was an issue for them. Because they tried to do something honest, and they were left with something that was this sector that violated an energy condition, this sort of Galilean crap.
They needed a jump to get rid of that stuff.
And you don't even bother by.
No, we do. I mean, look, we have models of a bounce, and we even have a matter sector. We just have been too lazy to write it up. And that matter sector blue shifts as you get to small scale factors and red shifts as you expand. And so
it's not the model that you and Surjit were telling me when you were here 3 years ago.
It is the brain gas. Yeah.
Okay.
Yeah. Yeah, I mean, the core aspect of that model is just that it is a form of matter. There are no NEC violating instabilities. NEC violation comes from.
I was hoping it was some other model. Okay.
We'll write the paper, or maybe a student will, and then you can judge. From the paper. But this solution of the cosmological constant decouples these two things.
Okay.
The balance is due to UV.
I'm
physics.
looking forward to your paper then.
Fantastic. So a rolling scalar field today will affect the equation of state of dark energy. And this is something then you can put constraints on the amount of, for example, kinetic energy stored in this rolling field. The rolling field better be very light. We're approximating as a linear potential around zero vacuum energy, but that means it has a very tiny mass, less than Hubble today, unless there are other forms of friction, which we'll talk about. And if we demand technical naturalists for this extraordinarily light scalar, then the kind of couplings we want are derivative couplings, axion-like couplings. And so we can couple to photons, for example, we can couple to fermions. And there's a constraint from the cosmology on the amount of kinetic energy for the dark energy, and it's not that much below the cosmological constant. It's roughly a 10% correction allowed. And you can ask, with couplings to various things, is there any possible way of direct detection of dark energy in this sense? Well, one effect is that if this scalar field couples to the actual photon, then a background phi dot produces an operator. That FF dual is a total derivative. So if you take the time derivative, integrate by parts, what's left of the photon is you're sourcing something that treats the two polarizations of the photon differently, in which case you get something called birefringence that causes a rotation of the polarization of light as it passes through this background. And what's then interesting about that is it will turn E modes, polarization modes that look like, for example, circles or stars, into B modes by doing slight rotations of the polarization of all of the light coming from, say, some region of the sky. And so that effect is already ruled out at some level because we haven't seen the B modes. And that current bound is already extremely constraining, that if the kinetic energy is an order 1 fraction of the dark energy, then that coupling F gamma has to be larger than M Planck.
David, let me ask you a question.
Yeah.
This phi, which is linear in time, it's as if you take away one derivative from FF dual. So it's as if you had a sort of Chern-Simons term.
Exactly.
So, this is like, isn't this also introducing like a gap when it's like when you have a Chern-Simons in?
This is
because it's like the kinetic term has two derivatives.
Yeah.
And isn't this like a mass term also? Besides the birefringence, isn't there also, no, it's quadratic. Yeah.
It's quadratic.
Isn't there
yeah.
also a gap?
It's A times B. I mean, it affects the.
Yeah, it's A times B, but we give it that in 3D,
it affects the
Simon
dispersion
uses a mass for the photon, right?
in 3 dimensions, but in 4 dimensions.
Yeah, I understand that, but this is like one less derivative. It's like an operator with one less derivative.
Yeah, it's linear in K. It's linear in the wave number.
You're saying this is not giving a gap. Yeah.
Doesn't give them. It doesn't. It changes the dispersion relation, but it doesn't give a gap.
It's like DGP. It's like a one derivative.
I'm
mass.
very sorry you said that, but okay, yes, it's like DGP. Fine. There's hope that future measurements, stage 4 type of pie in the sky measurements, could actually constrain this down to incredibly small numbers, down to almost 10 to the minus 9 for order 1 corrections in the equation of state, or 10 to the minus 8, say, within the current cosmological bounds, meaning 4 orders of magnitude above the Planck scale would be constraints on this F gamma parameter. If this dark energy is there. So this is already a very nice potential way of searching. Less effective in that it's just harder to do, but non-trivial way of looking for other couplings of this rolling scalar field to matter is through the derivative coupling to the axial current of fermions in the standard model. If you translate this into the non-relativistic theory for the fermions, this is effectively a gradient of phi dotted into the spin of the fermion. Now, of course, you have a homogeneous phi that's rolling, but we're moving relative to that rest frame, roughly 10 to the minus 3 relative to the CMB rest frame. And so that picks up then in that frame a gradient, which is of order the velocity of phi times phi dot. And so a 10 to the minus 3 suppressed effect is this coupling, if you couple the fermions in this way, would be coupled to fermions that you say do an experiment, and that sort of coupling, that grad phi, looks like a magnetic field in the sense that it couples to not the magnetic moment, but to the spin, and could be interpreted as a coupling to a magnetic moment. So if you can do an experiment where you can shield physical magnetic fields, then you can see potentially this magnetic field, which could couple to different fermions in different ways. It's not a magnetic field again. It would be this uniform background grad phi. It's challenging because it's a DC experiment, meaning it's just a constant background. And that means you need to combat very low frequency noise, basically drift of your spins. So it's hard. The nice thing, though, of course, is that the signal is coherent forever. And that always is a nice contribution. You're adding constantly the signal if you can get above the noise floor. But another version of this story is that because that grad piece gives you a velocity suppression, you could imagine taking your fermions and putting them in a storage ring and moving them at roughly the speed of light. This then boosted fermion would get without the velocity suppression, the same precession of the spin. And if you can set up the experiment, you can very carefully measure the precession of the spin by putting charged particles like protons in a ring at the magic momentum. You can potentially search for this signal as well. And these sorts of storage rings are already being proposed for detecting the electric dipole moment of the proton, but in a different configuration. You can now look for precession due to this other effect. And it just requires you to orient the spin perpendicular to the velocity, but parallel to the ring. And it turns out that this should give us some reach. The kind of reach.
Sorry, this is an effect that averages to 0 over a.
No,
no,
it doesn't.
No, but it goes around the ring.
It's around the ring. Yeah. No, it doesn't average around the ring because the effect is always in the direction of the velocity. And so the amazing thing is it doesn't matter which way the particle is going, that is your boost relative to the rest.
Okay. So can you explain the G-2 of the muon here?
I think the spin is oriented in the wrong way for the G-2, but I'm not sure.
But the G-2, well, okay, I mean, it's processing, it's, look, it is, you start with LFC, I mean, it's along the direction, then it doesn't matter how it is oriented. It just processes, right? If G is equal to 2, it goes exactly parallel to the velocity. If it is different, then there is a different velocity of precession with respect to the rotation in the ring.
Yeah, I just don't remember. Is the spin for G-2 oriented in the direction of the velocity or not?
I don't think it matters.
It matters for this experiment because there's no effect if it's oriented in that way. So, I
don't think it matters. Yeah. I mean, as long as there's
a perpendicular component to the velocity, then there will be precession.
Yeah.
I mean, for us to get sensitivity here, we need to be stable for 1,000 seconds in the storage ring. Now the parameters are different. Oh, we checked for the muon. Yeah, we checked for the muon for constraints from the G-2 experiment, not to explain G-2.
No, of course.
Yeah, no, good question. We checked for the muon. Maybe it's in our paper. Yeah, it could almost constrain it in principle, this coupling, because the muon, of course, doesn't. So let me show you the plot. Supernova 1987A, of course, already puts a constraint on massless or light particles coupled to the proton or nucleons, and this experiment can do a little bit better than that. You'd say, well, the muons, do they get a constraint from supernova 1987A? They do, in fact, because there is a density of muons during the supernova explosion. It's at a temperature which is not that far below 100 MeV. And so supernova 1987A already puts a constraint on F mu. And I think the G-2 experiment itself can't put a constraint on it because it's much weaker than that. But in principle, you could do a storage ring experiment if you focused on this and just barely perhaps get above the supernova.
Very good.
Yeah. All right. So anyway, this is a way of doing it. And it's a very cheap way of doing it if someone builds the storage ring to do EDMs for the proton. Another possibility, and something that actually makes the specific models I care about a little nicer, is if there's a different source of friction than Hubble. Namely, there could be some sort of thermal friction. If phi couples to some gauge sector, for example, then it's possible for that gauge sector to be populated and the thermal bath to effectively extract energy from the rolling field. The rolling field, then we're going to couple to a Yang-Mills group, but a Yang-Mills group that doesn't confine at the relevant energies. So this is a weakly coupled Yang-Mills theory. And what you can show, and I don't have the slides in this talk because I have a limited time, but you can show, as has been shown by Ricardo, your colleague, many years ago, that there is a contribution to the friction of phi rolling with a background phi dot, and that friction is proportional to temperature cubed, and then a long worked out proportionality to number of colors and alpha. But this then tells you that for certain parts of parameter space, it's possible that this friction could be more important than, for example, Hubble friction. So if you look at the equations of motion for phi dot in the upper left, g cubed is just the linear term. That's, v prime minus v prime. And the left side is the normal equations of motion in curved background, or FRW, but there's an extra term, that upsilon, which represents the new form of friction. If that upsilon is T cubed times some parameters, then you can ask what the steady state behavior of this system is. Does the dark radiation, this thermal bath, reach a roughly steady state value, as well as phi dot? And in fact, they do for a large range of parameters. And the steady state equations you can get by set phi double dot to 0 and rho dark radiation dot to 0, and you get these estimates for the temperature and phi dot. And notice the temperature depends on Hubble to the -1/7 power. So it slightly grows with Hubble, but stays very stable even over a Hubble time. And the point is that in this limit where the upsilon is much bigger than Hubble, where the thermal friction is much more important, you can estimate where the dark energy is. There's vacuum energy, there's energy in the thermal radiation, and there's energy in the kinetic energy of phi. And you find that in this limit, you're dominated, after the vacuum energy, you're dominated by the thermal radiation. So it's possible that that radiation, that friction on phi, is as hot as roughly a milli-eV, almost, again, almost the energy density that you would find in the cosmological constant. It's going to be roughly 10% or something. Those are the limits. And you can get into that limit as long as that F, that coupling, phi over F coupling to GG dual, is less than a TeV. So much less than a TeV means this is another sector. It's some hidden sector that phi couples to that strongly. The first effect of this is, if this is the version of friction you have for a rolling field, it actually, order 1 changes the evolution of the equation of state. It is from even quintessence. So it's a very different effect. And if you can actually get enough data points over redshifts from 0 to 2, then you can see distinction between this model potentially and normal quintessence, who relies on Hubble friction to describe its rolling. Now, you can ask, can the standard model couple directly to this radiation? Well, if it truly is a pure Yang-Mills sector, then the operators we couple to are very high dimension. So for example, psi bar, G squared is dimension 7 operator. Thus, these are going to be very hard to probe. But the dark sector can be very robust and complicated. It's the Yang-Mills coupling, their GG dual coupling, that gives you the friction, but you can thermalize a lot more depending on what is in the dark sector. So if the non-abelian group has fermions as well, those fermions could couple to us for lower dimension operators. If the fermions are charged under a dark U1, then we could mix with their dark U1. You can already have dimension 4. But regardless of what that dark sector is, there's a thermal bath, which is non-trivial, and it could be up to milli-eV temperatures. And we can ask then, what are the sorts of couplings we can have with that thermal bath, and how could we detect it? You could even construct a model where the right-handed neutrino couples to that thermal bath. And a right-handed neutrino, let's say one of the neutrinos is light enough, it's say milli-eV mass, that right-handed neutrino will become thermalized as a result of its coupling to this thermal bath. So here's a Yang-Mills thermal bath, or a non-abelian group with an adjoint fermion. It has a nice coupling to the right-handed neutrino. And what's interesting about that is at low energies, at late times in the universe, when the regular neutrinos become non-relativistic, then they're not in fixed helicity states. They're order 1, these right-handed neutrinos, which now couple directly to the thermal bath. And so that means the thermal bath could heat potentially to a higher temperature the cosmic neutrino background, to roughly almost 10 times the temperature of the predicted cosmic neutrino background, which means the number density of
you call this a neutrino because you assume that the neutrinos are essentially Dirac particles.
Exactly. I'm assuming the neutrinos are Dirac in this case. Now, if this radiation is part of the dark energy, the nice thing about it, not only could you potentially see it in its cosmological evolution, but you now have couplings to constrain, our couplings of the standard model to it. For example, if there is a dark E1 in there, we could have fermions in that sector be milli-charged under the standard model. For milli-eV scale milli-charged particles, there are no existing experiments, but there are plenty of upcoming ideas of how to detect milli-charged particles using electromagnetic cavities. If you want to detect milli-eV scale hidden photons, those are also going to be hard to detect. These are low energy photons. And we want to detect single events. So we have to leverage the work done for single infrared photon detection, which it's just now getting there, and use that to push down to lower frequencies the potential of single photon detection. It's hard, but there's a compelling reason for it. And then for neutrinos, of course, this signal is significantly better for Ptolemy or any tritium endpoint experiment that's trying to detect the neutrino background. But of course, it's a very hard experiment. So I don't know when it can be done, but at least it draws a line which is closer to the current capabilities. It's an interesting challenge for the detection community, and it's a broader statement that dark energy could be non-trivial in the way that dark matter is non-trivial. And we make the bet that dark matter may couple to us, and we look for it, have some compelling models and semi-compelling models. And here's a class of models where we could have direct detection of dark energy. Black holes.
David?
Yes.
Yes, just to tell you, we just spent 1 hour, and in principle, we have another 30 minutes, including discussion.
I see.
So if you can pace it, that we can have some discussion in the end. Thank you.
All right. Well, then I'm just going to say a few minutes about black holes and skip most of the slides, but they'll all be on the website, so you can look at them and send me emails.
I'd like to have you talk about the quantum mechanics part. I already gave a look on the slides. So
okay. So I won't talk much about black holes. The deep statement about black holes is that there's a problem with information loss from Hawking radiation, and I think it is compelling enough to say that we don't know how collapsing matter, when it forms a black hole, what it evolves into. And once it hits Planckian densities, there's no hard and fast rule that matter can't evolve back out of the horizon. And so because of that, just independent of whatever model you build, it's reasonable to at least look for tests of a non-trivial horizon. And then just one statement about that in terms of geometry, you might say, well, the surface of whatever that weird matter is can't come out because that's going backwards in time. You certainly violate GR inside of that ball, and therefore the motion is not dictated by the geodesic rules because there is a surface there and there are matching conditions. But you can just look in crustal coordinates and convince yourself that a shell can expand outward, and there is no experiment you can do in this case that violates causality. And it emerges always after it falls in, as long as you put a simple restriction on how the shell can merge out. So all of that is simply to say that it is worth doing the kinds of experiments that could detect non-trivial things at the surface of a black hole, even if it's a small chance of detecting quantum gravity. It's probably worth the effort. Quantum mechanics. In the 5 minutes I have, I can't possibly talk about this, but I'll give you just a little taste of it. Surjit gave a talk about this at Stanford, and it was 3 hours and 45 minutes. So we'll just do the 5 minutes, and then we can talk offline for 3 hours and 40 minutes. The deep thing to look out for is, can quantum mechanics be modified? Is it reasonable for it to be modified? The theory was built on observations in the 1900s, So who should say that's the absolute truth? Of course, we're always looking for deviations from the hard and fast rules. Quantum mechanics is the only known physical theory in nature that it is exactly linear. There is no other physical theory that's exactly linear. We teach electromagnetism and say, look, you can use superposition, but we don't work at energies where you can produce E plus E minus pairs in those freshman classes. And we ignore the Euler-Heisenberg Lagrangian. Quantum mechanics does not have any terms. It doesn't allow it, doesn't have space for it. It's just linear. It's a magical thing. It leads to the allowing us to ignore crazy thoughts about quantum mechanics being interpreted as a many worlds theory or not, things like that. In position space, the Schrodinger equation is this. You all know it. And in linear quantum mechanics, the wave function doesn't interact with itself. And so if it did, you would imagine that things like the Lamb shift would get corrections naively because the 2s and the 2p states of the hydrogen atom are degenerate to an incredible accuracy up to the Lamb shift, this tiny correction, even though the shapes of these wave functions are order 1 different. The no self energy of the electron cloud, the wave function with itself, doesn't then contribute to that shift. And you might think nonlinear terms would. Certainly another charged particle would be able to tell the difference between these two wave functions. Now, we want, I'm not going to discuss it in detail, but Weinberg wrote down a version of nonlinear quantum mechanics by just adding a cubic term to the Schrodinger equation in the wave function. And Polchinski showed that this thing violates causality, and you can see it by doing thought EPR experiments. And we just want to make sure that if we're going to modify quantum mechanics with a nonlinear term, we do it in a causal way. And there are very simple ways to make nonlinear theories causal. Causality, for example, is enforced by a Green's function, a retarded Green's function, which then sources produce effects from this time-dependent Green's function. Linear quantum mechanics itself can be written in a basis-independent way, but interactions, of course, are local. All of our interactions we write are local. That preserves causality. So the position basis is the natural basis. So if you let go of your strong desire need to be basis independent and you allow yourself to be in the position basis, you can write nonlinear terms. You use the position basis because it deals with the causality issue, and it's a natural embedding in field theory, which is naturally written in the position basis. X and T, they're all on the same footing, so almost. So this is very natural. Just go to the position basis, you write this interaction term, you make sure the interaction term is causal. If you have a Lagrangian quantum field theory, which is linear, and I don't mean linear in the sense of no interactions, I mean linear in the sense of it not depending at a higher orders on the state of the fields. We can talk about the nonlinear contribution by taking, say, a bosonic field in the theory and shifting it or adding to it in the interaction term alone by its expectation value in the state. And so if we take a Yukawa coupling, and to that Yukawa coupling, we add another term, but the term is the expectation value in the state that the system is in of the field, this becomes a new interaction of those fermions, the size. If we're in the Schrodinger picture, which is the easiest to think about the Schrodinger equation and state, then the operators themselves just depend on position and the chi fields just depend on time. So this contribution gives you a new contribution to time evolution that depends on expectation value of states. More subtle things that we're still working out the details of is you could do those shifts not just for a scalar field, but potentially a gauge field, potentially even G mu nu, even though it's hard to write down a quantum theory of gravity, say in the path integral or in some complete way that can take this into account, but we're working on that. But it's to say that you could imagine in principle all bosonic fields to be replaced by themselves plus their quantum expectation value, and then look for perturbative solutions to the system evolving with this extra epsilonic piece. Now that the weird thing is going to be, of course, that quantum state is if you imagine that everything is exactly where you think it is in all parts of the wave function of the full quantum state of the universe, then this background looks just like a classical background field associated with the normal photon or graviton or the scalar field. But if the quantum state of the universe is some linear combination of vastly different configurations of stuff, then that expectation value will be very different. It will be a measure of the average of all parts of the wave function, parts that we normally project away when we do the next experiment on our docket. If we want to talk about this in terms of time evolution, we can just think about this perturbatively. We can ask phi, what is the phi expectation value? It's going to depend on, for example, sources. The things that source phi in the epsilon goes to 0 limit are, of course, the fermions. If it's not phi, if it's the photon, then those are the charged fermions. And so you can write down the expectation value for that field by writing down the expectation value of the charge density of the fermions times the retarded Green's function. So if you go then to the one particle description, what you would imagine the causal one particle Schrodinger equation is taking the Hamiltonian, all in position space now, and adding a term which integrates over the full wave functions of potential sources for psi. In other words, the Green's function now represents that massless particle that can communicate from the wave function to itself. And because it is the retarded Green's function, this is a causal contribution. In addition, because that object, the second term there, is Hermitian, then you can also prove that the norm of the wave function does not evolve in time. It is constant, and so we can still talk about things in terms of probabilities. Now you'd say, okay, well, if I'm going to add a term like this, I should be worried about the incredibly tight measurements of quantum mechanics predicting correct results such as the Lamb shift. In fact, if you take a proton and you fix it to a point and you ask what is the energy difference between the 2s and 2p state due to this new self-interaction of the wave function, you could put a bound on epsilon of roughly 10 to the minus 11. However, this is not how the Lamb shift is measured. The Lamb shift, we cannot possibly pin the proton to a point or even to a location where we're doing Lamb shift measurements that is no bigger than the size of the proton or the Compton wavelength. The way we actually do it is we trap atoms and we populate both states and we look for that splitting from emission, but the atoms are now trapped either in a gas or in actual traps. But these trap sizes are never smaller than 100 nanometers, which is much larger than the size of the atom. And so that nonlinear term you can't separate the position variables of the electron and the proton. It's measuring the absolute distribution of this matter. And therefore, an atom where you are trying to measure very precisely the self-interaction effect of the wave function is weakened by how spread out the wave function of the entire atom is, not the electron in relative coordinates. And because of that, and because of the way they measure the Lamb shift, we suspect that the best bound you can get on epsilon from these measurements is 10 to the minus 2. And it's even a little suspect that you can get that good. In fact, the leading constraint on this, at least where epsilon is associated with charged particle interactions, the leading bound comes from the fact that we've trapped ions. And we've trapped ions in very shallow traps. And because of that, the ion itself could produce a self-interaction that would make the local potential repulsive instead of attractive. And so the fact that we've trapped ions, looking at all the experiments that trap these ions, you can put a constraint on this epsilon parameter of 10 to the minus 5. That's if it's positive. If epsilon is negative, then it's an attractive interaction, and we don't know. And it depends on more detailed properties of the spectral information about the trap. They probably can do close to the same bound, but we don't know. You'd have to reanalyze those experiments. I'll just mention 2 experiments that people are doing now, and then we can have the incendiary discussion afterwards about the broader implications of this. One experiment is being done, or one experiment that you could do is you could take an ion, split the ion, maybe not in space, but in energy levels of a harmonic oscillator that the ion is sitting in. And depending on how much of the wave function is in the ground state or the excited state, you will get different amounts of interference between the 2 parts of the wave function. And that will introduce a different phase, which now depends on the amplitude of the splitting, something that does not occur in linear quantum mechanics. So you split it, wait for a while, recombine it. There's an extra phase from this nonlinear interaction, and you can try to measure that phase. And currently, there's a group at Berkeley, Hofner's group at Berkeley. We've estimated they could get to sensitivities of epsilon of 10 to the minus 13. And they're starting these class of experiments right now. There are many complications, but this is already a signal that this very different sort of new physics will generate ideas for experiments that people can do right away with very dramatic reach in parameter space. The key point is that you can do a quantum measurement. I measure a spin. I either measure spin up or spin down. And as a result of that measurement, do something macroscopic. So if I measure spin up, I can turn on a magnetic field. Or if I measure spin down, I can turn on a different magnetic field. I can turn on magnetic fields, say, that oscillate in time differently, depending on whether I measure spin up or spin down, or point them in different directions, etc. And if I do that, then what this nonlinear term does is it tells you that we should be able to, in one part of the wave function, measure what ourselves, the experimentalists, did in the other part of the wave function, turning on a magnetic field when we didn't turn on a magnetic field. And a squid should be able to pick up magnetic fields in that other part of the wave function. You could even do experiments for gravity, where you have a gravity gradiometer, and the experimentalist measures a spin. And if the spin is spin up, they park their truck to the left of the gradiometer. And if it's spin down, they park it on the right. And from that, they measure the gravitational potential of the truck. And the nonlinear term in principle should be able to detect the gradient from the truck in the other part of the wave function. The opposite of the worry of, what's it called? I'll say it later when I remember the word. You can do macroscopic things if you amplify a quantum measurement. That's the bottom line. There are a set of experiments being done by Sushkov's group in BU, where not magnetic fields are using electric field and measuring extremely tiny voltages. And they also hope to be able to do perhaps 10 to the minus 11 sensitivity on epsilon, but with a totally different type of experiment. And like I said, similar tests could be done by on the gravitational version of this coupling, moving trucks, heavy masses, things like that. So my conclusion is just that we have this beautiful machine to look for potentially deeply motivated new physics at high energies. It's effectively many experiments, and so we should be thinking about many ways to look at very weakly, low energy, precise, but interesting, direct and dynamical stuff that could come also out of deep, if not crazy, possibilities. And that's it.
Thank you very much, David. Sorry, we have to rush in the final part.
I'm sorry.
I invite questions from everybody. And in particular, if you have questions on the black hole part, of course, we'll have a precedence. Raise your hand if you can, or just, okay, I see one raised hand from an email address that is hard to read. So please go on.
Oh, your sound is off.
Yeah, you have to unmute. Yeah, camera is open, but microphone is not.
Okay.
If you have any problem with the microphone, you can also write in the chat and I will read the question.
Yeah.
Here we go.
Yes.
Please.
Do you hear me?
Yeah, now I hear you.
Yeah.
Yes.
Do you know any estimation of the changes mass of nucleons on scalar field?
You mean the Mossbauer type of experiments?
Yeah.
Yeah, good. These.
Yeah.
Do I know the bounds on those masks? Corrections?
Yeah.
Is that what okay. Off the top of my head, no. I maybe read it off of this plot. Essentially, the bound comes from the precision at which, this measurement is coming from the precision at which you can do the Mossbauer experiment, which depends on the width, but also on shot noise. The bounds, so the actual, there's no precise predictions for the mass of the proton, or the precise predictions for the mass of the protons and neutrons are not nearly the level at which you could put a significant constraint on this scalar field. Here, what we're taking advantage of is the fact that if you change in the experiment the mass of the nucleons, even by a very tiny amount, I think I'm trying to remember what the numbers are. Let's say 10 to the minus 10, 10 to the minus 12, things like that. Then you can change the energy levels by a non-trivial amount. Yeah, so probably it's not 10 to the minus 12. Let's see, this is a coupling of EV for the Mossbauer. So versus GV, so that's 10 to the minus 9 effect. So roughly a 10 to the minus 9 effect is what we would be able to measure. And it's
minus 9 EV?
No, 10 to the minus 9 times the proton mass.
Oh, I see. Thank you.
Sure.
Yeah, everybody, please just open the microphone in case you don't find the button to raise your hand, or if you do find it, please raise your hand and I will give you the microphone. I don't see raised hands or microphones open yet. So maybe I can ask David for a clarification
Sure.
about this quantum mechanics nonlinear quantum mechanics. I was under the impression that if you take a Klein-Gordon equation and you do the non-relativistic limit, you get exactly Schrodinger plus corrections due to the approximation you made.
Yes.
Now you propose to modify Schrodinger, and now I was wondering if I go backward and I try to reconstruct Klein-Gordon, should I get anything different from the usual Klein-Gordon, or even in the relativistic equations now I expect to see some new effects?
Yeah. Well, you do expect new effects. It's a bit of a long discussion, but it's true what you do when you go from Klein-Gordon to regular quantum mechanics, you get additional terms. And in fact, the equation I wrote down for one particle is a well-known equation. There's a Schrodinger-Newton equation. And the point is that that equation is relevant for example, Bose-Einstein condensates, situations where there are many particles in the same state. And so what you're taking into account is the fact that there are additional interactions between the wave function in a sense and itself, but it's really a particle-particle interaction. And so this modification that we've added from the one particle description is something that would occur in a one particle system, in a rigidly one particle system. Now, in the field theory, what we're adding is something which is state dependent. And you can ask the question, where does the Klein-Gordon equation come from? So we're all taught field theory, start with a Klein-Gordon equation, tell us that there's some non-relativistic limit, but it's a little weird because there are antiparticles that you didn't take into account, But in fact, the field theory first satisfies the Schrodinger equation. There's a Schrodinger equation for field theory. There's a state which describes all of the fields. There is a Hamiltonian operator which dictates the evolution of fields. And what you can do is take that description and you can turn it into a path integral by inserting, the way we do from the operator language to the path integral language, inserting complete sets of states. The complete sets of states that we insert could actually, in fact, be coherent states, very classical-like states. And in doing so, it is very natural to generate or to immediately see that the Schrodinger equation predicts the Klein-Gordon equation or any classical field equation which comes out of quantum field theory. So I would say that the way that we're forced to think about it now, because we've added this nonlinear term, is to start from the Schrodinger equation in the field theory, rederive standard field theory language from the Schrodinger equation and see where the nonlinear terms appear. And so one way you expect them to appear, we're working out the details, is you can imagine a path integral, and the path integral is weighted by an action, and the action has all of the normal terms in it. Now there's no operators, they're just functions of space-time, but there's an additional term in there which is sourced by an expectation value of one of the original operators. And that source depends on the full state of the system. If the system itself is in a classical state, meaning the full wave function of the universe is describing a classical state of the fields, then that expectation value is whatever it is the field itself, but it is the background classical solution to the field equations. But if, for example, the actual state of the universe is me having turned on a laser in this room, plus the other part of the wave function, me turning on a laser in a different room, then the expectation value of, say, the photon field that appears in that action is the expectation value of that entire wave function, that entire state, which includes both electromagnetic fields. And so the classical extraction of things like the Klein-Gordon equation or classical field equations we'll have some very strange object sitting in there. And that strange object will be the expectation value of the field summed over, averaged over all parts of the wave function, whatever the wave function is doing. And so that term at leading order in epsilon is also derived by a path integral, but a path integral computed in the state, not the part of the state that we care about because we're in that part of the state, but in the full state of the system. And so operationally, you would calculate the expectation value of the field in what you think is the full state of the system. And then that would be a background field source to your path integral, where you calculate now dynamics on top of that. It was a long-winded answer, but does that make any sense? Oh, you're muted.
I think it does to an extent, but yes, I need to a little bit to digest it.
Sure.
But it resonates with another question I had in mind, because again, from this modified Schrodinger equation, I think I should expect as well that the exponential decay law for unstable particles is no longer accurate. So do you, and this is a very quantitative thing that
yes,
anybody can test with a huge bag of atoms that can decay. So
yes,
I don't know how small is the epsilon you had in mind, but this is a pretty established law. So I was
that's good. But yeah, the issue is that the epsilon effect on, say, that decay. Yeah, very good. So the effect on decays like that are not just proportional to epsilon; they're proportional to the wave function overlap of the particle with itself. And the frequency associated with the decay. So there is some suppression due to that. Let's see, I can't think of what the actual effect would be.
I was thinking a stupid thing, that the exponential it's the only function that tells you that in whatever interval of time you do observe the particle, there is always a given fixed amount of probability that is just a constant over time.
Absolutely.
The moment you change the differential equation, you get another function. This is no longer true. So precisely because now it depends on psi square, you must observe different lifetimes in different environments. So if you have a busy experimental room, you will observe busy of these decaying atoms.
Yeah.
It will, if they're very packed, you will see a different lifetime than when they are just an isolation.
Yeah, what I'm saying is that let's say you don't have the nonlinear term. Of course, the busy environment, if you're looking at a gas and they're decaying, or whatever environment you're doing your experiment in, there is a background that affects the properties and therefore affects the time evolution. That's already there too. What you really then want to ask is, if I add an additional term, which is the self-interaction, what is the strength of that self-interaction compared to the energy associated in the Hamiltonian? And that depends on the localization of the object that is decaying, essentially. And whether that contribution from the localization of the object itself acting on itself, if that's stronger than the background interactions with other fields and particles, then yes, it can have a stronger effect. And in principle, you could measure something. But you know, a particle moving around, say in a gas in a large box, and say maybe even scattering or things like that. Well, I guess scattering is more complicated, but in a box with some background field, and that you can still describe the time evolution of that state, you'll predict the lifetime, and the lifetime depends a little bit on what's going on in the background. And so this simply adds a background to that. But I'd have to think about a specific setup to be able to calculate what that is. I mean, we did look at long lifetime experiments, and these contributions are small, because they're being compared to nuclear energies, essentially. So the fact that the wave functions are so spread out means that nonlinear term has a 1 over r in it. That's what the Green's function is. And the 1 over that r is the length scale associated with the spread of where the particle is when it decays, its own wave function. And so that 1 over r gives you a scale, essentially. And that scale is very small compared to, say, MeV. And so it doesn't affect, it's a very tiny effect on nuclear decays, for example. I mean, you just want to sort of order of magnitude estimate what is the size of that Hamiltonian term, that extra term, right? And there are wave functions squared in there, integrated over volume. So that's just, it's the wave function normalized, but now spread out over the whole volume. And then when the particle decays, it's somewhere in that volume, but its size is, nuclear size, whereas the wave function is spread out and normalized over a much larger volume. So the local interaction at that point is small. That's what I'm trying to get at. I mean, it's why that a lot of these precision tests, there were many precision tests of Weinberg's theorem. It's because there was no Green's function, because there was no understanding of separation of variables in his paper. And Polchinski did understand it and explained what sort of terms were ruled out by causality and what sort of terms would not be ruled out by causality. But those other terms now really depend on the spread of the wave function of the entire system and not just the single object. For example, the single nucleon in a nucleus. That distance is compared to the location of the nucleus, because the nucleus wave function is very broad. And so it's an overlap with the wave function squared that you're getting a suppression by.
Yeah, I think I appreciate better now what's the fact you're after. Anyone else? Physics question on the many frontiers we heard about. Okay, we decayed a little bit, half of the audience in the meantime.
Well, it's time to get a drink, I think.
It is time, maybe, for at least this time zone. It wouldn't be a bad idea. But since you mentioned at the beginning some sort of sociological issue that everybody is betting on the same horse.
Yes.
And this is essentially the phrase that triggered me to invite you to give this talk when you were giving your comments at GGI. I don't know. Maybe, yes, let's suppose we all had one drink already and we are more willing to say things we wouldn't have said before the drink. Do you want to elaborate on that? Because
I'll just say one thing.
I agree with what you say, but at the same time, it's a free market. Physics runs on free market. You cannot force people to do things. Everybody chooses what they think is best.
You cannot. My argument with John was that he saw deep reasons to go after the LHC, and I think no deep reasons to go after anything else. And that is a very subjective point of view. And his complaint was that many young people are not working on the LHC. Many young people don't care about the hierarchy problem. And I think it's important for young people to think about the hierarchy problem, but I think it's also important for them, many young people, not to contribute to the same horse, as you say. And there's a lot of people wasting time in this field is the problem. And I think it's just lack of confidence, that you think, well, if I go over here, what are the chances that this thing will work out or be interesting, or I'll ever get a job, or things like that. Some of those are really practical things, but many of those things are just I don't want to waste my time. I don't want to look like an idiot, something like that. And I was very motivated by the group at Stanford, Surjit and Peter Graham, Savas's gang. What really struck me about them is they would spend years on the same problem. And so the one proposal for an experiment they had was this Casper experiment for axions. Casper is the only experiment that is measuring, looking for axions based on its coupling to QCD, which is the only reason why we care about axions. It solves a strong CP problem. Every other axion experiment is going after the electromagnetic coupling. So to me, that's a very deep statement. And it took them 5 years to come up with that idea. They had a first idea, which was molecular interferometry, that took them a couple of years, almost works. And then a couple of years later, they realized with squids and aligning nuclei spins that you could actually get a big enough signal in principle if you do the work. So the whole point is they thought about that problem for years. And my concern is that the thing people think about for years is what model of supersymmetry is going to be okay? How are we going to extract new physics from the LHC? How are we going to get deeper into the WIMP dark matter or space? But it's fine. Those are important things. But if you look, it's not necessarily the most interesting thing. It's not that interesting, I think, in the broadest sense. And if people thought about the hard problems for years, they will come up with ideas. They just have to dream about it at night. They have to suffer thinking about it. That's all I'm sort of advocating. And so when John is complaining that nobody's thinking about the hierarchy problem, I get that. I agree with him, in fact. But that John is complaining that people are working on small scale experiments or non-LHC things. Yeah, maybe the motivations for some of the experiments are not very interesting, but not all of them. And it's a healthy sign that people are looking for where the interesting things are. All the evidence we have so far is that there's nothing at the LHC. Save, there are B anomalies, they're very interesting. I hope something's there. We should look for it. People should fight very hard to get that. I think that's very important. But it's just that, it's just an anomaly. It's interesting, it may go away. There's nothing anymore pointing to this energy scale at the LHC or the 100 TV collider that says, my God, something has to be there. If we learn that there's nothing there and that the Higgs is a little bit more fine-tuned, some people, the old school people, the Ramans, the Johns, the other people of the world, will say that's very important that it's fine-tuned to 10 to the minus 6 and not 10 to the minus 4. Okay. Young people might not find that very interesting. And that's not because they're not deep or not bold. It's because maybe it's not interesting. And 100 TV collider is great because it's a universal push to high energies independent of why motivating it. It's a threshold, a frontier we know is there. So do it. But don't argue for it based on deep reasoning. When I imagine most of the deep problems are not solved at 10 TeV. And maybe there's zero information about those problems at 10 TeV. If you worry about fine tuning, cosmological constant is insanely fine tuned. And so we have a trick for the Higgs. It's just called fine tuning. So I don't, if you want a different model for the Higgs, sure, that's possible. But you're not, it's not necessary. That's what I think. But Ricardo's gone, so, I can say everything I want, and it doesn't usually look like that. I'll say a few things, and then he'll yell at me, but.
You're still on tape, eh? Don't.
I'm on tape, but he's not going to listen.
But while you were talking about Ptolemy, actually, I thought that maybe every experimentalist should have a little Ptolemy in their life, alongside with another maybe more secure project.
I think so.
And the same should be true for theorists. That maybe you should have an alongside thing where maybe you risk more.
Right.
I'm not so sure we encourage even the younger ones to actually take this attitude. We probably do not do that enough.
Yeah, I think it's crazy. We're in a crazy business. This is, and people act like bankers. It doesn't make any sense. We're doing something really crazy, and almost everything we all do will be completely irrelevant at some point, unless we get very lucky. And so why aren't that? Everybody should be acting a little bit more like that. You can say, well, big experiment, responsibility, da, 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 da. Okay, 50% at most to be responsible if you think that's important. But at most, you can't, most of your week, majority of week is spent on things you should do. You're not going to succeed. I think it's just, young people should know that. It's risky from top to bottom. We're not bankers. So.
Can I ask a question?
Hey, Strumia.
So these crazy modifications of quantum mechanics, so in general, not what you discussed, but I know other people,
Sure.
Is there anything that can be said about how they depend on energy? So is it good to search them at low energy or not?
Yeah, good question. Look, they depend on sensitivity to quantum effects and locality, I would say. But because you want this thing to be causal, so that's going to depend on local interactions. Yeah, is there a sense? I mean, one thing that occurs in this is you could naively think that energy is not conserved. You can lose energy into the other worlds, or the other parts of the wave function can source things in our part of the wave function. And so that energy non-conservation naively is there, but the full theory does have a conserved energy associated with it.
So I am asking now, the most sensitive experiment is something, is a low energy experiment, or again, it's convenient to go to high energy?
I see what you're saying. Yeah, high energy, like you can say the LHC. So something we thought about a lot is the LHC, you smash particles together. It's a quantum event, a purely quantum event. That means the full wave function is the particles are spreading out maybe spherically if it's an S wave, but a particle hits specific points in the detector. Can that S wave now trigger something else? Now that we have this, it's a source. It's a coherent source. But it turns out that this effect, at least, well, for general nonlinear cases, that could be important. The problem is that the wave function of the protons that are hitting each other are not localized to 100 MeV. They're localized to, say, micron or something like that. They have broad wave functions. And so the thing that always dilutes the nonlinear effects is the spread of the initial states in their interactions. And so really what matters is the physical quantum effect, like in interaction, and the spread of the initial wave functions. That ratio is very important for sensitivity. If the spread of the wave functions is very close to the interaction size, you maximize the effect. But that's independent of energy. I don't know what energy that's the easiest to do at, but that's what you have to achieve.
Thank you.
Sure.
Any more comments?
Could I ask you a small question?
Yeah, of course.
Please.
Thanks for the very inspiring talk. I had a question related to your discussion about nonlinear quantum mechanics. So if I understand correctly, the interpretation of the measurement relies on the many-word interpretation. And basically you are thinking that all the different branches are being at the same physical place and you're averaging over them when you discuss the following evolution.
Right.
Do you think it's a line of thought that should be investigated better? Like, should we be brave enough to try to think about such a crazy and complicated direction, which like puts into question some basic principles, like even the idea of having a statistics of measurements. Like it's hard to compare and to assess probability, to assign probabilities to something that doesn't even live in the same space, in the same world. Do you think we should even be so brave to go beyond what we are used to, even in that direction?
Yes, of course. I mean, if that's the question, the answer is just yes. But I think, let me say something about many worlds and maybe a mistake that's been made historically. You know, what occurred to Schrodinger cat, toy, you know, thought experiment, was that this is the prediction of quantum mechanics. That if a measurement is made, there's an entanglement between the measurement and the thing being measured. That's just a result of quantum mechanics. And the difficulty in measurement, the difficulty that comes up and causes these people to meet, otherwise very intelligent people to meet and to panic about it, and Copenhagen interpretation and consciousness, is it important or not? All of that is the obsession we all have and have to have as human beings with the I, that I am measuring this. I should be able to say what I'm measuring, et cetera, And in a sense, the many-world interpretation is a Copernican move. It is saying that my thinking conscious self, but is just a part of the wave function. And quantum mechanics predicts that. And measurement is not distinct from any other interaction in quantum mechanics. So measurement is, you take two subsystems, you move them close to each other. The Hamiltonian tells you how to evolve it, and then you move them away from each other. And now you have me having measured this and me having measured that, and making decisions based on that, where I'm going to dinner. That is just a consequence of quantum mechanics, not any extended anything else. People try to comfort themselves by adding things so that they don't have to think about that, or that goes away. I call those the disappearing universes interpretation of quantum mechanics, because quantum mechanics predicts that distribution and we don't want to think about it. And we even want to say that there's a physical reason why that goes away. So people have already simply adopted that new addition to quantum mechanics, so they don't have to think about it. And all I'm asking is, quantum mechanics is linear. It was this equation written down, and then people interpreted it and panicked, and they just didn't go very far after that. And along the way, a few people have written down terms which show that there's some possible way to consistently write down nonlinear interactions. If those nonlinear interactions are there at any level, it means all of the other worlds are physical. But the other worlds in field theory is just a distribution of fields. It's a description of the physical state of the system, which includes all parts, both what we are strongly entangled with, and I mean by we as in this part of the wave function, versus the rest, that other versions of these fields that include the measurement, the measurer, the device, everything. They have full distributions. And nonlinear term just means that all of that interacts at some level. And so on the equation level, we haven't done anything crazy. We've just added the next order term, the obvious next order term, in a way that you can add it in field theory first, make it local, and then it's causal. Asking what that implies is crazy. I mean, the result is crazy, but that's not crazy because of this term. It's crazy because of quantum mechanics. And it was a decision just not to think about it because it didn't matter. We just apply a projection operator, do our experiment, not think about, renormalize our state, everything's okay. The fact that just adding a nonlinear term to field theory in a causal way creates insanity is interesting. It's interesting on its own. And you can ask questions about, if that term is there, would we still see the world we see now? And in fact, there are many reasons to think we would. Inflation, for example, produces many universes by quantum fluctuations. And so we're a tiny, tiny part of the wave function if you believe cosmic inflation occurred and sourced matter by these fluctuations. But the quantum state during inflation was very close to the Bunch-Davies vacuum, which is a homogeneous isotropic state, which means that the average value of fields, the expectation values of fields, have nothing funny in them. They're just some background, which at worst is time dependent, assuming the universe had a beginning. And so that means that inflation gives you an attractor solution that local experiments on the Earth don't see nonlinear quantum mechanics. Even if there is nonlinear quantum mechanics, even if it could be there, because all of the average value of the wave function, the expectation value of all fields, is become almost trivial. And so that's interesting too, that adding a nonlinear term, there's natural reasons why we haven't discovered yet, because the universe kind of wants to dilute it, the effects of this nonlinear term. So for me, that thing, wow, my God, that's another reason to think that these terms are naturally there. We've just ignored them because they feel crazy and we haven't seen evidence. But then you have to think in all versions of the story, whatever is diluting this effect, where can we still see it? In the example I just gave you, if inflation dilutes the effect, we would see it cosmologically. We would see this distribution of universes at the cosmological scale, because while it's homogeneous and isotropic average, if there are enough universes averaging, it's time dependent still. And there's potentially something which is like a fluid out there, which is just comes from this background. The fluid might seem very nominal, but it might be a natural consequence of something crazy, nonlinear quantum mechanics. So for me, it's just the fact that you are allowed to write down this term. It doesn't violate anything. There are even natural reasons to think that you wouldn't have discovered it. It could be tested. So I'm not then from there trying to reconstruct a new mathematical system of all of physics, which magically reproduces everything we already have. I'm just asking, what are deviations that are allowed, and how do we test it? And this is one which requires tests which are extraordinarily different than normal tests. And it would be foolish to not at least try to think about what those tests would be and what it implies. It may be hard. It may be that there's a struggle in being able to fully interpret this modification in a field theory. But we spent 8 months on it, and it's much more sane than we expected it to be. So that's.
Oh yeah, I agree with the general attitude. I find it's an interesting challenge that in order to make some sense of the theory, you need to rely seriously on this many-word interpretation, which is, from the philosophical point of view, it's a big step. Like,
yes,
to me, it seems like going a bit against the empirical attitude of physics, because it's hard to really say that you can measure something repeatedly if every time you do the measurement, you're actually branching in a different direction. It's kind of a subtle.
It is, and it is that we define physics by the measurement itself, but that takes us out of it, that it separates us. And we already knew for 100 years that we can't separate ourselves out of it. So, but what's very interesting is that if there is a nonlinear term, instead of preparing a state and measuring it 10,000 times to see a distribution, you can prepare a state, measure it once in many different ways, and you can see all parts of the wave function. So you can potentially get closer to proving something or motivating something which you can't prove from quantum mechanics, which is the Born rule, where probability comes from. And if you can do a single measurement and measure the distribution of a wave function from one measurement or from a series of measurements, but preparing the state once, it's a very different measure of the properties of the system. So, you know, in some sense, yes, there's the personal conscious I'm measuring, and that, you know, there are other parts of the wave function that's doing something else. Okay. But on the other hand, you can prepare a state once and actually see how it's distributed if this nonlinear term exists. So I have mixed feelings about the philosophical implication. I mean, I think it's clear there are philosophical implications. I think they were there from quantum mechanics to begin with. And if you're working hard scientifically to avoid those philosophical implications, that's one motivation. But if you're working hard to think about how to test those implications, that's it seems like it'll be more fruitful. At least it's what I'm interested in.
Thank you.
So we are 30 minutes past the time we were initially supposed to finish.
Excuse me, Roberto.
And, yes.
Excuse me. No, this is Francesco. May I ask a very, I'll take
Sure.
the opportunity to ask a very naive question, actually. But
How can I say no to that?
no, but I also had 2-3 drinks already, so I can
Okay.
I don't know, very naive question, actually. But do you think, is there any possibility that actually the evidence for dark matter is actually an evidence for the, let's say, presence of the multi-universe, multi-world, let's say?
Yeah, good. So we are, one of the directions we've been thinking is if there is a nonlinear term in the Schrodinger equation or in the field theory that depends on the state, then even a few little quantum fluctuations will distribute matter in different universes or different parts of the wave function differently. And it's possible in principle, if that nonlinear interaction is associated with gravity, that matter, which is just normal matter, but in a different part of the wave function, could be another source of gravitation and therefore could be effectively dark matter. But it takes some work to build the model that does just what you want. And then there's a little annoyance, which is that the wave function is normalized. So it'll never be more than order 1 times the dark matter, unless epsilon is 5, but then I don't know how to, then it's hard to do it perturbatively. So, but yeah, we have thought about it. We have thought about it.
You.
Not in public until now, but yeah.
Okay, great. Thanks.
Sure. Good question.
So I guess we had food for many thoughts. I would like to thank both Adam and David for giving their talks.